This is an Algebra 2 lesson, and we're going to be looking at finding the value of the natural base e. E is a number like pi. Pi, remember, is 3.141592, and it goes on and on and on. So e is like pi in that it's a decimal approximation that continues without pattern or termination. It's also an irrational number. The interesting thing about e is that it shows up naturally in our compound interest formula when we compound the interest or growth continually. That is, the number of times we compound the interest keeps going more and more and more times. In this activity, we're going to actually find an estimate for the value of e by examining how the growth factor in our compound interest rate formula, that is the 1 plus r divided by n, changes as we make n very large. To simplify our calculations and to see the pattern easily, we're going to start with $1 invested at an interest rate of 100% for a period of just 1 year. Recall also for our rules of exponents that if I take a base of m raised to the a times b power, that's the same thing as m to the a quantity to the power of b. So we can take a look at our compound interest rate formula, which is P, principal, times the quantity 1 plus r divided by n, where r is the interest rate, and n is the number of times each year that the interest is compounded, to the power of n times t, where t is the number of years. It can be rewritten when we split these exponents as p times our quantity 1 plus r over n to the n, and that quantity raised to the power of t. So in our situation that we have right here, our value for r is 100%, or in decimal point 1.00. Okay. Our value for p is our starting value, and we're going to start with a grand total of $1. So p is equal to 1. And we're going to look at it over a period of just 1 year, so t is also equal to 1. So our compound interest rate formula then, our rule becomes a is equal to 1 times 1 plus 1 over n raised to the power of n and then raised to the power of 1. Or simplified, this just becomes 1 plus 1 over n to the power of n. We're going to look at what happens with this as we compound the interest more and more frequently over this period of the year. That is, we want to make n very large. So let's take a look at some of those values, and we might need our calculator for that. So let's go ahead and pull that out if we have it. Okay. We're going to fill in the table of values below, and we're going to choose larger and larger values of n as we go until we get a really large number for n as your last value in the table. Okay, so n equal to 1, that's not very interesting. As I substitute 1 in here, my a is going to be just 2. Now let's see what happens as we make larger and larger numbers for n. So we're going to be working with this, over a period of a year. Maybe we want to do it like every month. So maybe n is 12. It's not real large, but it's a little large. So let's take a look at what that would look like. It would be 1 plus 1 divided by 12, all raised to the power of 12. And we get 2.61. And we'll put a few more decimals out there. Okay, but that's really still not a very large number for n. What happens if I do it every day? So like n could be 365 times in a year. So let's see what that looks like. We have 1 plus 1 divided by 365 raised to the power of 365, and that gives us 2.71457. We'll throw a few more decimal points there. But still, that's not really very big. Let's pick a larger number for n. Let's pick 500. Okay, so let's see what happens with that. I have 1 plus 1 divided by 500 raised to the power of 500. And we get 2.7155, and we'll go 7 here, rounding it up a little bit. Yeah. Not a whole lot of change between these two, but a significant change with our first one. So it looks like maybe we might be leveling off to a value. Let's pick a next value. Let's pick n equal to 1,000. 1,000 times a year, you're going to add on your interest. So we have 1 plus 1 divided by 1,000 raised to the power of 1,000. And we get a number fairly close to our previous one, 2.71692. Let's go higher. Let's go 5,000. Let's see what happens if we do 5,000. 1 plus 1 divided by 5,000 raised to the power of 5,000 gives us 2.71801. And one more. Let's go out to 10,000. So we have 1 plus 1 divided by 10,000 raised to the power of 10,000. And in this case, we get 2.7181. Okay, these two values are the same through the thousands place, 2.718. So going out to the thousands place, we see that our value of A is getting closer and closer to something near 2.718. That's an approximation for our value for E. In fact, our calculator has a couple of places where it has E on our calculator. On the left-hand side, right here in the blue key, it's a second function. We can get powers of E. And over here on the right side, above the division key, we have the value for E itself. So let's take a look and see what our value of E is on our calculator. See, it's a lowercase e. That's what it shows up as. And it comes out to be on our calculator 2.718281828. And that number really continues to go on and on and on. Actually without pattern, even though it looks in our decimals here that we have somewhat of a pattern with the 828. But it doesn't keep that up. It will change as we go through. Okay. So that's what our value of E is. And in our next lesson, we're going to look at functions or graphs of functions and how to work with this number E.